Okay, so this is from this Field et al. Paper from the 2007 cruise that we did from essentially Queen Charlotte Sound all the way down into Baja. And what we plotted here is the depth at which the aragonite saturation threshold has fallen to corrosive levels. And ordinarily out in the open ocean, this depth is great. It's 200, 400 meters, something like that. And what you can see, you get up on the shelf, is that these depths are anywhere from 0 here, we actually have corrosive waters at the surface on this Point St. George line, the Oregon-California border, to 80 meters along the entire shelf. So the entire shelf, now remember the shelf break depth is about 200 meters. So the entire shelf from Vancouver Island to Baja is seeing water that is corrosive to aragonite. And in some places it's more intense than others, right? But it's there everywhere. And if you were to look at cross-shelf sections, here's the density profile. Here's this 26.5 water that I talked about that comes up. This is from this line 5 here. This is a real intense expression. And here's the aragonite saturation threshold. Here it is out here. Offshore, it's about 150 meters. And as you come in, it rises up to the surface right along with the temperature of the other uplying signatures. Okay? The pH, I've been trash talking about pH and how it's useless, but just again, for reference here, we've got numbers that were up over 8.2 in the surface from the high productivity and the consumption of CO2, and numbers that are down below 7.7 in the upwell source waters. Okay? And that's driven by the carbon dioxide chemistry of these waters, the dissolved inorganic carbon in the CO2. Most of that is natural. Okay? This water takes 50 years to get here. There's been a lot of respiration. It hasn't seen the sun. There's been no photosynthesis. It hasn't been able to ventilate with the atmosphere. You add a lot of carbon dioxide when you respire material for 50 years, and that drives the saturation levels down by purely natural mechanisms. But there's a little bit of extra that comes from anthropogenic CO2 sources, and we can talk about how that's calculated if you want to. And that's enough in most of these cases to be what pushes the water from just a little bit on the good side of the threshold to the corrosive side. Okay? And now for the bad news, back to this picture. We know it takes a long time to get there. We're not exactly sure what the path is. I think it was maybe 40 or 50 years to get here. What was the carbon dioxide content of the atmosphere 40 or 50 years ago? A lot lower than it is today, right? So that means that the water that upwelled here in 2007 saw the 1957 atmosphere, right? The water that upwelled in 2009 saw the 1959 atmosphere. Now, it's not that simple. But what you can see is that even if we stopped anthropogenic CO2 rise today at 390, the water that's on its way here, this train has left the station. And we're not going to be able to say, oh, hey, you stop. Okay? Right? So the anthropogenic CO2 signature has already been impacted on these waters. Right? And there's just not much you can do about it. Okay. And I'm getting closer, so those of you who've gone all the way to sleep should start stirring there. But there's more to it than just rising CO2. Right? When you go back to this oxygen section from 2001, and you look at the CO2 section, PCO2 or CO2 mixing ratio, on the same two sections. So here's this hypoxic water. Here you see it in the very high CO2. Here you see the hypoxic water because of respiration, natural processes, and it goes right along with greatly elevated CO2. Okay? So yeah, degradation of organic matter over the upwelling season depletes oxygen, drives the carbon dioxide up, causing more corrosive condition, and therefore these things are completely linked. And if this is a trend, as Francis and Jack and Jane, as others suggested in this 2008 science note, where they showed that this is the data before 1980. This is the data before this is up to 1999. All of the data they could collect up to 1999. The green is the data from 2000 onwards, and you're starting to see these lower levels here in nearshore waters. And here's 2006, okay, which was the last really extreme hypoxic event. And there's been some suggestion that this is not just variability, that this is actually a trend. This is in fact a trend, and we've not got just a hypoxia issue, but a corrosivity issue as well. Okay, is there any good news? Now there's probably lots of folks here who know this better than I do, but there are calcium carbonate forming organisms that live in conditions that we know are corrosive to the mineral that comes around, right? Freshwater mussels. You go out and stand in the Willamette River. The bottom of the Willamette River is covered with freshwater mussels. That water is undoubtedly undersaturated with respect to this mineral phase. The water, the interstitial water in mudflats and tide flats, very acidic, certainly corrosive in a purely thermodynamic sense of these minerals. And yet you can go out and dig a clam pretty much any time you want to. So these organisms must have coping strategies. So maybe that suggests that what's going to happen is that the organisms can develop coping strategies, or that what we'll see is rather than sort of wholesale crash of calcium carbonate forming organisms, that there will be selection for the organisms that do have a strategy and discrimination against the ones that don't. And essentially, we get the treat of having this experiment done for us off our coast. And in probably a sense that is not the case for almost any other environmental problem, we're kind of in at the ground floor. You know, we know this is coming. We've started to look for it. We're seeing the effects. And it looks like we've got the opportunity to really do monitoring and development of indicators that show stress from acidification, or enhanced corrosivity. Maybe this is going to be the place that tells us, okay, this is how the ocean is going to change. These are the things we can do in the way of mitigation strategies. Right, so this is this sort of silver lining to this cloud, that we may have a real opportunity to predict and respond to this issue. Okay. So ocean acidification, which, you know, is a horrible name. I kind of like enhanced corrosivity, but that sounds really scary too. It's happening. You know, there's just really no argument about the basic chemistry of this. It's going on. It's going to keep going on. We've got surprises in place for us. When you go to places like the Oregon coastal ocean or the upwelling Cascadia margin, that are particularly sensitive to these kinds of perturbations, at least with respect to this notion of solubility of biogenic minerals. The Oregon coastal ocean, when it's functioning properly, right now, this is kind of a variable system, so it's hard for us to say what's the normal operation. But when it's functioning properly, it supports this massive productivity in response to upwelling, huge fisheries in response. It takes atmospheric CO2 it takes CO2 out of the atmosphere. It appears to stick it back in the deep ocean where it's gone for very long time scales. It's this really efficient system. And it does all this while most of the time managing to avoid extreme hypoxia and corrosivity. Because of natural processes, upwelling source waters and chemical processing, we're right on the edge of these issues all the time. Right? Something can go a little bit wrong and make things go from great to terrible in the course of a year plus or minus. Hypoxia and corrosivity are inseparable. Right now I'm distinguishing corrosivity from acidification because acidification is technically defined as this anthropogenic CO2. But if you call it corrosivity, changes in chemistry that make biominerals less stable, then hypoxia and corrosivity are just going over. If there is this climate change linked to hypoxia, there's some very interesting ideas about why there might be that link. Then there's also going to be this climate change linked to enhanced corrosivity off our coast. And this natural variability, I don't know if you call it a canard, but it's this natural variability doesn't mean you don't have to work. It means that actually pushing some of these things to our doorstep maybe sooner than we thought it would. But it's giving us these opportunities to study how systems respond. And then I want to just wrap up